how it will be acquired in the flow cytometer. And once you acquire in the flow cytometer, what happens is every particular cell which has been stained with the fluorochrome tagged antibodies will be hit by the laser, and the signals are captured by the detectors. So you know this already, which we have seen all through these days with the lectures. So once the detector captures the signal of every cell, finally the software which is attached to the system, the flow cytometer, physically collates this data and gives you as data. Okay, and that particular data you need to analyze and give a report out of it. So that is our job. So now today's class will be seeing about this data analysis. Before I proceed, any doubts with anything you want to ask, any doubts or something regarding last class or any doubts? Okay, fine. So let's start. So data analysis, the output file from the machine. So you have a flow cytometer, okay, and the flow so you process the sample, stain the sample, and run it in the flow cytometer, which is called acquisition. And once the flow cytometer does its analysis inside, it gives you a data or as a file format. Okay, so this file given from the flow cytometer is called a flow data file, and it can be of two types. One is FCS, that is flow cytometry standard file, and other is LMD file, which is list mode data file. Okay, so whenever you want to share a case for an opinion to your colleague, a flow file or a case, flow cytometry case you want to share with your colleague or someone, you will be sharing only these files. Okay, it is called the FCS file. FCS stands for flow cytometry standard. Okay, it's a FCS file. The other file is, the other format of that particular flow cytometry file is called list mode data file. Okay, some instruments give the output in this format, and many other instruments use data output in this format, which is called flow cytometry standard file. Okay, so this is just an output from the machine. Okay, so this is the flow cytometer, and it is connected to a computer physically. Okay, so this particular computer has a software which will give instructions to the machines. Okay, so you can able to give instruction to the machine via this software which has been interfaced with the hardware. Okay, so once the analysis which is happening inside this particular flow cytometer machine will be displayed here, and finally after the analysis is over inside the flow cytometer, you will get a final analysis file which will be of two format. One is FCS file, the other is an LMD file. Okay, so I told you the abbreviation of expansion of FCS, which is flow cytometry standard file, which will be the output file in most of the flow cytometers. And there is something called, and the other format is called list mode data file, which is the output file of a certain instruments like Beckman Coulter Navios or FC500. Okay, so these two differs. Okay, now coming to the softwares. Okay, so there are two types of softwares to analyze these flow cytometry files. So what I mean to say is that, like, you see, this FCS LMD file is like a, for example, I'm telling you, it's something like a video file. Okay, now the video file you can open through many softwares, correct? You can open it through Windows Media Player. You can open it via VLC Media Player, or many softwares are there to open such videos. Right? Similarly, these two files can be opened via some softwares, and through that software only you will be analyzing the data. Okay, so that software is again two types. One is the acquisition software. So when I say acquisition software, it is the software which is connected to the hardware physically. Okay, so when you buy an instrument, you will also get a computer with a software installed in it. That particular software is called acquisition software. So this software will be giving commands to the machine. So you will be giving command to the machine via this software. Okay, and similarly, when the machine is analyzing and showing the data, it will be showed in this particular software. So it is also called acquisition software. Okay, now so the same acquisition software, post acquisition, you can use it for analysis. Okay, so even you can use the same default software which comes with the instrument to do the analysis, and that particular software is called acquisition software, and you can also do analysis in that. Okay, so if you have a flow cytometer, you know the system which is attached with it will have a software. Okay, so that is called the acquisition software, and the acquisition software can be used for analysis. Okay, then you have other softwares which are not connected with your instrument. These are actually only analysis software. It cannot be used as an acquisition software. What I mean to say is that you cannot use these software to give instructions to the machine. Okay, so these are all independent software which will be used only for analysis. Okay, or this software will be a third-party software. That is, it is not connected to your instrument or your manufacturer at all. Okay, so example for these softwares include Kaluza, which I am working on, and I'll be showing you at the end of this particular lecture the Kaluza live analysis. Then there's something called FaxDiva. This is a BD company software. This is a Beckman-Coulter software. Cytobank is another software of Beckman-Coulter. Flojo is another software. So these are all third-party software which will be used only for analysis. Okay. So the advantage of these softwares, when you compare acquisition software and these softwares with respect to analysis, these softwares have an extra features which makes it more superior than the acquisition software. Okay, so they have some added features which makes them special. So I would love to analyze my flow cytometry file in Kaluza because I have some advantages in it compared to the acquisition software which I have in the system connected to the flow cytometer. Okay, so there are some advantages like enlarging rare events or few events. I can able to enlarge them, but that particular features may not be available in the acquisition software. So to make it very short, you can use the acquisition software for both sample acquisition when you are feeding the sample in the flow cytometer, and also to give instructions to the flow cytometer, and you can use the same acquisition software to do analysis. Whereas the other software which I told you, like Kaluza, Diva, Cytobank and Flojo, these are all just analysis software. Okay, you can just do analysis with this software. Okay, and they have some added features compared to the acquisition software. Right? Right. So any other doubts? Like you have any doubts now? Okay, now. So I'll be discussing about some tools which will be used in analysis. And I have taken this from Kaluza. But almost all flow cytometry analysis softwares have similar features. Okay, so there are tools like drawing plots, something like histograms, to generate an histogram, to generate a dot plot, generate a tree plot, radar plot, density plot, contour plot, overlay. Okay, so these are all some of the plots the options are available in the software, but I would be using mostly 4 types of plots, which is the histogram, other is the dot plot, then density plot and contour plot, and overlay plot. Okay, even contour I use very rarely. So the most commonly used one is histograms. So I'll be showing you a live analysis at the end of this lecture. So I'll show you how a histogram is drawn, how a dot plot is drawn. All I'll tell you that. Okay, so this is histogram, dot plot, density plot, overlay, contour plot, so and so, so and so. Similarly, you have other things like gating the population, like polygonal gates, rectangle gates, elliptical gates, Boolean gates. So these are some of the tools which we'll be using in the analysis. Okay. Now let's go with the plot type. So first we'll cover this particular area. So which is plot types. Okay. So the plot types may be of histogram, dot plots, density plots, contour plots, and radar plots. Okay. So again, I'm telling you the most common plots are histograms and dot plots. Third comes the density plots. Okay. So anyone knows what is the difference between an histogram and a dot plot? Have you come across the word histogram? Anyone? Have you come across the word histogram? Is histogram a word new to you? You can unmute and you can talk.
No, sir.
Histogram is not very, you have heard about histogram, right? What is histogram?
Sir?
Yeah, histogram. Yes, Dr. Pallavi. Yeah.
Sir, histogram is the same one which we get in the CBC analysis.
Perfect.
Which has a proper graph.
Okay.
For example, for RBCs and all, we can see the size of the cells.
Great. What cell count are you using, doctor?
Sir?
What automated analyzer you are using in your laboratory?
It's Beckman DXH 800.
Excellent. So you are getting histograms in that. Even
Yes.
I use the same system. Okay. So you have seen histograms. Have you not seen a dot plot there?
In dot plots are also there, sir.
Perfect. So what is the difference I'm asking you?
So in the dot plot, what I know is we can see the events in that. The way we say in the
Populations. Correct. But tomorrow morning, what you do, you go and have a look at it. The difference between histogram and dot plot is that
Okay.
a histogram is the one which has, by default, count on the y-axis.
Okay.
Okay. So when you want to see an analysis histogram, any histogram, if you open on the y-axis, by default, you will have count.
Okay.
On an x-axis, you will have a parameter.
Okay.
It could be size. It could be, I'm going to talk about flow language. So let's keep that. So for histograms, basically count on the y-axis. X-axis, you can have a parameter. It could be a scatter parameter or it could be a fluorescent parameter. So only x-axis carries the parameter, whereas the y-axis by default is count. Whereas if you take dot plot, both x-axis and y-axis will carry the parameter. So if you see a DXH dot plot, you will have volume on one side and scatter on the other side. That is called VSN technology. Okay. So a dot plot is the one which has parameters on all its axes, both x-axis, y-axis, or if it's a three-dimensional dot plot, you have one more parameter on the z-axis. Whereas an histogram is always has only one parameter on x-axis and y-axis by default is count. Okay, so that is the difference between an histogram and a dot plot. Okay, I'll show you an example. Now density plot, I'll show you an example. Okay, so now this is the one. So here the x-axis is a parameter. So I'm showing CD45KO. And as I said, you histogram by default has count on its y-axis. Okay, so this is a way of expressing 45KO in a histogram. But with respect to a dot plot, I can use one more parameter on the y-axis. So I have used a side scatter here, but I can use any scatter parameter or even a fluorescent parameter on y-axis. Okay, so this is histogram is a representation of one parameter. When I say parameter, it includes both fluorescence and scatter. Okay, so how many parameters you will get in a 10-color flow cytometer, or how many parameters you can explore in a 10-color flow cytometer? Anyone? Just give a see. I want you all to be very
Parameters.
sorry.
12 parameters.
Excellent. You will have 12 parameters. So 10 mark colors and 2
And forward and side scatter.
Excellent. So you have 12 parameters. Okay. So that's excellent. So everyone understood, right? So even scatter is a parameter. Okay. Is Dr. Bishal there today? No, he's not there today. Fine. Because you, unless you don't duplex it, because he had a doubt with duplexing. So I just asked whether he's there. Right. So that is about histogram and a dot plot. Okay. Histogram which measures or compare only a single parameter, because y-axis is by default as count on it. And dot plot which compare 2 or 3 parameters. If you are using a 3-dimensional plot, it's 3 parameters. If you are using only 2-dimensional x and y, it's only 2 parameters. Okay, so that is the difference between a histogram and dot plot. Now what is a, so this is what I told you, count on y-axis. Whereas in a dot plot, you have parameters on both axes. So now coming to the density plot and contour plot. This is density plot and contour plot. What is a density plot? Density plot is nothing but a dot plot. But this gives you an added advantage of concentration of the population. See here, if you see me, if you see this dot plot, there is good amount of events, they are forming clusters, but I don't know where they are concentrated, where the particular population is concentrated. Now, there is one more difficulty where if I want to select a population or draw a region around a population, now I don't know where are the borders, where is the population exactly lying. Okay, so I don't find a clear demarcation between the populations. But when I use a density plot, you see that it's a dot plot. It is very similar to this, but it can also give you an idea of the concentration of the populations at different areas. Now I can clearly say the majority of the neutrophils are here. The majority of the lymphocytes are here. Of course, there are some hematogones, but there are lymphocytes are here and erythroids are here. Now, if I want to get only the lymphocyte population, I can easily draw a region like this. Correct? See how beautifully it is demarcated. In fact, the stage 1 hematogones is so clear. So I can able to clearly draw a region around the lymphocytes. If I want to select only the erythroids or I want to draw a region around the erythroids, I can easily draw a region around the erythroids. But here, the demarcation is not that clear. So that is the advantage with a density plot. So density plot is nothing but a dot plot with an advantage of showing concentration of the populations, where it is much concentrated. A contour plot is something which shows only the areas where the population is concentrated. So you see here, this is the advantage with density. Density plot shows both features of dot plot as well as concentration. Whereas if you see here in a contour plot, I'm not seeing any events, background events. It is just showing. It's something like you would have seen this forecast, weather forecast, right? They normally present their data in a contour plot because they show only the areas where it is highly concentrated. So I can say that there are 1, 2, 3, 4 concentrated populations in this particular plot. Okay, I have no idea about the background population. Okay, so this is lymphocyte population, this is erythroid population, this is neutrophil population, and this is, what is this population hitting the wall? Anyone? Eosinophils. Okay, this is eosinophils, high side scatter. Okay, so this is how it is. Now, so if I want to select the lymphocytes, I can also use contour plot to select the lymphocyte. But the problem with contour plot, what I have is, I have no idea about the background population. Say, for example, there is if you are dealing with a case of leukemia and your blast is very small percentage, say for 4% or 5%. Okay, if you use only the contour plot, you may miss it because those small populations are not seen anywhere. Whereas if I use density plot, still though I can have an idea about the concentration of different populations, even that small population I can able to pick it out. Okay, so that is the problem with the contour plot. Contour plot just gives you an idea about the constant populations that are good in number, and it shows the concentration where the areas where the population is very concentrated. Okay, so that is about the contour plot. Now you see, this is the density plot. So the density plot also shows you, it's a dot plot, where it shows all the events which are singly scattered, and also it shows cluster, and also it shows area where it is highly concentrated. Whereas a contour plot, as I said you, it just shows only areas where it is concentrated. But these events are missed here. And unfortunately, if you have population of interest which is lying in this area, with only these few scattered events are your population of interest, then you will be missing in when you use contour plot. You will be missing it when you are using a contour plot. Okay, so that is why we don't use contour plots in rare event analysis. Okay, we will not use it in rare event analysis where you want to pick up 50 events, 100 events, some small number of events. Okay, in that case, we will not use a contour plot. Contour plot is used when the population density is high. Okay, for rare populations or populations that doesn't form a cluster, we will never use a contour plot. So I don't use contour plot much. I use histograms, dot plots, and density plots. Okay, and this is one more plot which is called radar plot. So as I said you, a dot plot can show you around 2 parameters or at the maximum 3 parameters if it's a 3-dimensional dot plot. This is called a radar plot, okay, which can show you any number of parameters. all you need to select is, it will ask you how many parameters want to be shown. You select all the 10 parameters, it will show you all the 10 parameters. Okay. We don't use it regularly during our analysis. Okay. But when you want to present the data somewhere, say for example, you want to publish your data or you want to show your data in some conference. Okay. In that case, you can use this thing. You need to use this because nowadays papers or journals want you to present your data in a much high dimensional forms. So for that, this can be useful. Okay, this is called radar plot, not much used during our routine analysis. Okay, so any doubts about the plots? Any doubts about the plots? Crystal clear? So we have finished about the plot. So you know what is histogram, you know what is a dot plot, you know what is a density plot, what is a contour plot. Okay, you know what is a radar plot. Okay, overlay, I'll tell you what is overlay. Tree plot is something to show the hierarchy, that I'll cover it later. Okay, now let's go to the type of scales. So you have scales, right? So I told you this is y-axis, this is x-axis.
Sir,
And yeah, please, yes.
how to analyze this radar plot, sir?
Excellent question, even I don't know. Okay, so that is very tough. Even I'm not getting it. I'm not understand. I've tried a lot of times to learn it, but still I didn't. Okay, to be honest, even I am not getting it. Once I get clarity, I'll let you know. Okay?
Okay, sir.
Because I've asked many people who are more experienced in flow cytometry than me, but I couldn't get the answer yet. I don't know what. If you learn from someone, please let me know. Okay?
Okay, sir.
Thank you. So coming to the types of scale. So you know what is a scale? Scale is something like the graduations present on the x-axis and the y-axis. Okay, so here you have 0, 50K, 50,000, 100,000, something like that. So these graduations are called scales. Now these scales are of three types. One is a linear scale, the other is a log scale, and other is a bi-exponential scale. Okay, now what is the difference between a linear scale, log scale, and a bi-exponential scale? I'll tell you. Now, when you want to show a data which is within a smaller range, or when you want to show a parameter which is of a smaller range, you can use a linear scale. So linear scale is something like the graduations are at an equidistant interval. You see here 0, 50,000, then 1 lakh, then 1,50,000, then 2 lakh, 2,50,000. So they are separated in an equidistant manner. Okay, and when you use a linear scale, you can able to show a parameter which is of a not a very high range. Okay, you can use it for showing a parameter which is of a narrow range or which does not differ much. Okay, which for example, can you give me an example for a parameter which does not differ much in range, or some? I mean, like it should be within. It is not with a very broad range, with a broad dynamic range. It should be in a narrow range. Can you tell me any parameter? Any wild guesses? Cell size. Okay, forward scatter. Correct. See, in clinical flow cytometry, what is the smallest cell and the largest cell you analyze? Smallest cell may be a platelet. Correct. Correct. Maybe around 2 to 3 micrometer. And the largest cell you analyze may be around 30 micrometer maximum, right? Or if you want to work with some other thing, maybe 100 micrometer. So the distance here is from 0 to 100. So that's a smaller range, and you can easily show that in forward scatter. For example, you can put a graduations of say like 0 to 20, mean 0, 20, 40, 60, 80, 100, and you can cover the entire populations within that particular graduation. Okay, so that is a linear scale. So linear scale is something if you want to show a parameter which does not have a very wide range. Okay, on the other hand, there is something called log scale which will be used. Okay, you know what is linear scale. Now, linear scale is where graduations are in a equidistant manner, in a linear fashion. Okay, 0, 50,000, 100, 1 lakh, 1,50,000, something like that. Now log scale is somewhere where the graduations which are shown is in a logarithmic fashion. So you have 0, 100, 1000, 10,000, lakh, something like that. Now when do you use a log scale is when you want to show a parameter which differs by a wide dynamic range. The example for that is all your fluorescent parameters. All your fluorescent parameters. For example, you take any fluorescent parameter, you have a population which is negative for that particular fluorescent marker. And you have a population which is bright for that fluorescent marker. Now if you see the difference between these two, the negative population it may be 0 or negative. But the positive populations may be so many fold, say like 1,000-fold or 10,000 times brighter than the negative, times greater than the negative population. So you cannot cover that dynamic range with a linear scale. So you need a logarithmic scale. And to cover that, we use log scale. Okay. The other scale I'll come later. So now linear scales are more effective for displaying data sets with values spread evenly across a given range or a narrow range. Okay. When working with flow cytometry data, linear scale is commonly used when plotting forward scatter and side scatter. So linear scales are commonly used for scatter parameters because even side scatter, you take lymphocytes, not much side scatter, and the maximum side scatter is from eosinophils, right? So this does not have a very wide range. It has only a narrow or a given range. So you can use side scatter in linear scale. Okay, so side scatter and forward scatter are related to cell size and cell granularity respectively, and they can be used in linear scale. But linear scales are less practical when the data points consume a larger dynamic range, as with fluorescent markers. Okay, so for example, if you take anything, say like a CD19. CD19 is negative in all the populations except B lymphocytes, and the B lymphocytes will express bright CD19. So the dynamic range is very high, and you cannot show that particular marker in linear scale. If you show it in linear scale, one population will be there within that scale, and the other population will be out of the scale. You cannot even visualize that population. So that is why we use log scale for fluorescent parameters. Okay, like cell of interest is signed with a fluorescent dye. Positive cells that contain the larger number of target structures. Okay, that means here positive cells means it's a cell which contains the antigens to which the complementary antibodies are added. Okay, emit light sometimes at an intensity thousands or 10,000 times higher than the negative cells. Okay, so log scales are suitable for this type of parameter. Clear? Now see, this is the fluorescent parameters, and if you say you need to show the fluorescent parameter in linear scale, this is how the data looks. Okay, where the negative population has been completely out of the scale. If the other way around is, you find only the negative population in the scale and the positive population may be out of the scale. Okay, but if you use a log scale, you can cover both the populations within the scale, and that is why we use log scales for fluorescent parameters. Okay, there is only one exception to this rule. Anyone want to give a wild guess? When we are analyzing one particular parameter or thing with a fluorescent marker, we may not use log scale, we use like linear scale. So I told you, like for any fluorescent parameter, we'll use log scale, right? But
Sir,
yeah,
is it enumeration assays?
Enumeration assays, basic enumeration assays, we like, see, enumeration, you use the beads, right?
Yes, sir.
So beads basically will give you the count. Normally beads will not, I told you this, beads will not take up a fluorescent space. It will never take up a channel.
Okay.
A dedicated channel to it. The beads are designed in such a way, the enumeration beads are designed in such a way that they will be bright for all the channels. So every channel has it, but it will not interfere with your data because it is very bright and it falls somewhere outside. So it will not interfere with your analysis, and you don't have a dedicated channel for enumeration beads. See, I'll tell you what it is.
DNA ploidy.
Perfect, super, ploidy. Excellent. So the ploidy is the one which will have a fluorescent marker in a linear scale. The reason is, I'll tell you what. You see, take this. Now, if in a ploidy or a cell cycle and the ploidy analysis, the cell which is in G0 phase or G1 phase will have 2n chromosomes, correct? When it goes for S phase and then comes to G2M phase, the chromosome number doubles, so it becomes 4n. Okay, so now the range is somewhere between 2n to 4n. You don't have 10 n's or 1000 n's or 10,000 n's here. So the range is very, very narrow. It should be either 2n or it should be 4n. So it should be x or 2x, correct? So in such a case, since the range is very narrow, you can use a DNA ploidy dye like propidium iodide or or even your FX cycle violet. These are all ploidy dyes or DNA binding dyes. These DNA binding dyes, you can see them in linear scale than log scale. See, when I'm saying that you should see it in linear scale, it doesn't mean that you should not see it in log scale. You can see, but the resolution differs. Okay, when you see it in a linear scale, you can see the beautiful separation between the G0, G1 cells, the cells showing S phase, and the cells that are showing G2M phase. But when you see the same populations in a log scale, the same ploidy in log scale, still you can see G0, G1 and G2M phase with S phase, but the population is, the plot is more representable. Like the graph or the histogram, this is cell count right on the y-axis, so it's a histogram. So this histogram is more, the histogram which is better when you express the DNA binding dye in a linear scale when compared to a log scale. Okay, now you understand when to use a linear scale and a log scale. Clear? Any doubts? Any doubts? To make it very simple for you, all scatter parameters, better to see it in linear scale. You can also see in logarithmic scale, but again, the separation between the populations may not be that clear when you see in log scale, the scatter parameters. All fluorescent markers, it's better you see it in logarithmic scale because the populations differ from each other by a wide dynamic range. So it's better you see it in logarithmic scale. If you see in linear scale, one set of population will be there in the plot, the other set may not be seen in the scale at all. It will be falling outside the scale. One exception to this rule is DNA binding markers, because again it's very narrow. Either you have 2n or 4n, not beyond that. Even if it is going to be super high hyperdiploidy also, it can be 6n, nothing beyond that. Okay, so the range is quite narrow still, so you can use the fluorescent dyes for DNA binding dyes, fluorescent markers in linear scale. Okay, now the third plot which I told you is, first is linear scale, then logarithmic scale, and third is a bi-exponential scale. Now this is the scale which we commonly use in analysis. The beauty with bi-exponential scale is that the linear scale and log scale, okay, the bi-exponential is a hybrid scale where you can combine the features of linear as well as log scale. So it's a 2-in-1 scale. How does that happen is, at near the reflection point, it behaves like a linear scale. What is a reflection point? Is more likely a zero. That is a point where the population starts. Okay, so at that area, this particular scale behaves like a linear phase. So if you see here, see this is a log scale. Okay, and this is a bi-exponential scale. You see this is log scale, 0, 10 power 0, 10 power 1, something like that. But if you use a bi-exponential scale, you see this area, it is a linear scale, -5, 0, 5, and then log scale starts. So near to the reflection point or near to 0, it will be a linear scale. And beyond that reflection point, it will be a log scale. So these bi-exponential scales are also called as lin-log scale, that is LIN, which stands for linear, and log stands for logarithmic. So it's also called lin-log scale. It's also called hybrid scale because you are using both linear and logarithmic scale in this. It has both features of linear and logarithmic, so it's called hybrid scale. It is also called logical scale, LOGICLE, logical scale, and it's also called bi-exponential scales. So this is the thing. So bi-exponential scales are bi-exponential are equations that are characterized by, we would have studied this in mathematics, bi-exponential. So bi-exponential are equations that are characterized by exhibiting a pseudo-linear like behavior near a reflection point in flow cytometry, mostly 0 or a negative value, and transitioning to pseudo-logarithmic behavior at values distant from the reflection point. Okay, near to the reflection point, it's linear, which is, I don't want to confuse you with the linear reflection point. Near to 0, it's linear, and away from 0, it's logarithmic. That is the feature of bi-exponential scale. So these equations are often used to display flow cytometric data with high dynamic range as log scale. Okay, but when you use log scale for showing data with high dynamic range, you see that there is some population lost. Here you can find there is some populations which are falling inside the scale. I mean, we cannot able to visualize them. Similarly, here also you find there is some population which is going below the scale, and you cannot able to visualize this. This is not compensation. Remember, compensation will be in a skewed fashion. Again, here also something. But when I adjust this particular both the scales to bi-exponential scales, now what happens? This population comes inside. Now you can see the entire population clearly within the scale, because now this area becomes a linear, so all this population will be coming inside. Okay, and this is all same as logarithm. Here it's same, almost same. Only in this area it will be a linear scale. Okay, now this is very useful when the data values are below 0. So when it is below 0, linear scale and log scale cannot show you the data. But when you use logical scale, you can able to see the data even when it is in negative region, or even when it is below 0. So that is the beauty of bi-exponential scale. Okay, I repeat, near 0 or near the reflection point, it acts as a linear. It acts in a linear scale, and away from the reflection point, it acts in a logarithmic scale. So it has both linear and log features. Hence, it's called as lin-log scale, or a hybrid scale, or a bi-exponential scale, or a logical scale. Okay. So see here. Now you find. So this area you find a linear scale, and this area you find a logarithmic scale. That is called, the other name is lin-log scale. Okay. See, now this is the same thing I'm just explaining you, the bi-exponential scale. You see this particular population is out of the scale. We cannot able to visualize it because here it starts from 10 to the power 1. Okay, now if we convert this area to a linear scale, we can see this population. So when you convert to linear in this particular reflection point, you see the population easily coming in. Okay, so to make it short for you, almost all your dot plots or a 2-parameter plots, you need to see it in bi-exponential fashion. Because in linear, in log scale, there will be some population which will be buried, or you cannot see, which will fall outside the scale, and you cannot able to visualize them. So you need to see them under bi-exponential scale, so that all populations are within the scale and you can visualize them completely. See, if it is like this, there may be a diseased population or an abnormal population lying inside or below the, away from your scale, and you can miss them. So when you use the bi-exponential scale, everything comes inside, and you will not miss anything. So that is the use of bi-exponential scale. Okay. See now, so this is a logarithmic scale. Now your software is well equipped. So if you just select and able to drag in, all the population will come inside. So this is a classic logical scale, and this is how we adjust. So there is a population which has been buried inside. Okay, what I need to do, see, I just do that. Just check my cursor. Now if I'm going to pull it like this, all the population will come inside. As if I'm pulling, if I'm pulling upwards, all the population will come up. Okay, so I'll show you during the analysis. You just remind me. So that's how you need to pull the population inside. So this is a typical bi-exponential scales. Okay. Yeah. So any doubts with scaling? There is 2 chat box questions. Sir, in density plot, do different colors represent different population? No. In density plot, different colors represents the concentration. So I'll go back. That's a good doubt. Now, see, this is a density plot. Okay. Now, different colors does not determine any different population. See, this is neutrophils. This is lymphocytes. This is erythroid or RBC population. Now, every population has pink color. Does that mean they are all different. Now, so what these colors mean is the intensity. If you first take red is the area where that particular population of cells are very concentrated. Second is green. So the concentration decreases from red to green to blue and then pink. Okay, so it depends upon the concentration of cells. If you see this particular granulocyte or the neutrophil cluster, it doesn't have any area where it is concentrated, the red color population, because it is not as concentrated as lymphocytes in this region. So the concentration is not that dense. So you have green. So it's just showing where the population is much concentrated. If it is red, highly concentrated. Then it's green, moderately concentrated. So something like that. Okay, thank you. Any doubts? Any other doubts? Shall I go for quadrants? If you have any doubts, please unmute and ask your questions. Okay, now coming to quadrants. So quadrants is something what we draw to set up a negative limit with the help of internal negative control. So for example, I want to analyze a population and this is a negative internal control. I just plot this, I just gate this particular population in this particular plot and then I adjust the quadrant in such a way that the negative limits are set. Then I'm going to gate the population which I'm interested for or the study population, and then with where that population falls, I'll interpret. If the population is falling same in this negative area, then I'll call it as negative. If it is falling here, I would call it as it is positive for the x-axis marker. If it is falling here, I'll call it as positive for y-axis marker. If it is falling here, I'll call positive for both x and y-axis marker. Similar to that. So now see, if I've gathered a population like this, okay, across two markers, CD5 and the marker. Now the population lying here is negative for both these. The population lying here is positive only for CD5. It is negative for this x-axis marker. And the population lying here is positive for both CD5 and a x-axis marker, which is activation. Okay. So that is about the use of quadrants to set up a negative limit with the help of internal negative controls. Now the other advantage with using quadrant is if I want to see how much of these cells, see if the complete population is lymphocyte and I want to check how much of the lymphocyte population is expressing CD5, then to check that percentage also I can use quadrants. Okay, so I need to gate the lymphocyte population in this particular plot. Then I have to draw the gates with internal negative control, and after drawing the quadrant, setting the quadrant, I will gate the population, target population or population of interest, and check how much of these particular population or cells are expressing CD5 and give it as a percentage. Okay, during analysis, I'll show you how to check the percentage also. Okay, someone has to remind me during analysis. So I have to tell you about the quadrants and percentage, and then I have to also show you the logical scale adjustments. So please remember, and if I'm going to forget, please remind me. Okay, and there's another type of quadrant called hinge quadrant, H-I-N-G-E. Okay, hinge quadrant. This is used when you see here the population is very clearly falling in line. So I can able to put a quadrant with straight axis. But sometimes what happens, the population will be lying in this fashion. It will be like slightly encroaching into the other quadrants. If you draw this type of straight gates, straight linear quadrants. Okay, something like this. Now if I want to draw a linear quadrant like this, now see, I have to draw like this, right? So some amount of this population will be cut, which is not right. So I will use a hinge quadrant where one among the arms can be adjustable. Similarly, this arm can be adjustable. Okay, that is when I'll be using a hinge quadrant. Okay. And one more use of quadrant is that it can be also used as a gate. For example, now after seeing this population, I am only interested on this particular population for further analysis. Then I can use this quadrant name as a gating for gating this particular population. For example, this is Q1, Q2, Q3, Q4. Then in the subsequent plot, I can select to show only the Q3 population. Okay, so I can also use as a gate or select the population for further analysis. I'll tell you what is gate in the subsequent slide. I mean, like we are in the upcoming slides. Okay, gate and these things I'll describe. So you know what are the parameters. So whenever a signal hits the detector, you will have a pulse generated like this. The pulse has many things, like one is the height of the pulse will be recorded, the width of the pulse will be recorded, the area of the pulse will be recorded, and the time of flight of the pulse will also be recorded for every parameter. Let it be a side scatter, let it be a scatter parameter like forward scatter, side scatter, or a fluorescent parameters. All these things will be recorded for each cell, for each fluorescent marker. Okay, so you see how much data is generated. For one particular cell signal hitting the detector, a pulse is generated. Okay, the pulse is different for a scatter, forward scatter. A pulse is generated is different for a side scatter. A pulse generated for every fluorescent parameter is a different pulse. And similarly, for one cell, these many pulses are generated. And you are going to analyze around lakhs of cells. And so many these signal pulses will be generated. Okay, now this particular pulse which is generated, as I said, you has different indicators. Like, see, there is a height of the pulse, width of the pulse, area of the pulse, and then this is called time of flight. Time of flight. Okay, so that is also there. So for example, if you want to take any parameter, you have that particular parameter in these denominations. For example, if you have forward scatter, you have forward scatter height. If you want forward scatter width will be there, forward scatter area will be there, forward scatter time of flight will be there. You need to select which one you want. Normally we use area. Normally when you are analyzing, we'll be using area. When do you use forward scatter height? When do you use forward scatter height during our analysis? Anyone? When do we, you mean like I told you, like for fluorescent parameters and scatter parameters, mostly we'll be using area, right? Area, or which is otherwise called as integral. Okay, but is there anywhere during a routine analysis we use forward scatter height in a plot?
HLB27.
Why HLB27? HLB27 is again a parameter which is stacked for fluorescent marker. So you can see it in area. Height is specifically seen. I discussed this during our lectures. One of the universal plot to discriminate a population, we use height, forward scatter height versus forward scatter area.
So singlet.
Singlet. So only in singlets we'll be using height. Okay. Only for singlets we mostly use height. Okay. Beyond that, during our routine clinical flow cytometry, we'll be using only area. We'll be only interested in area of the signal. Okay. So you know what are the parameters? So in case if you select, you will have multiple parameters. You will have forward scatter area, forward scatter, which is also called integral, forward scatter height, forward scatter width. Similarly, forward side scatter integral, side scatter height, side scatter width. Similarly, for fluorescent channels, FL1 integral, FL anything. So if you have 10 fluorescent parameters, for every 10 fluorescent parameters, you have denominations in integral, height, and width. Okay, so you need to select which you want. Now, most commonly we'll select area, except the singlet plot where we select height and area of forward scatter or any other thing. Okay, now coming to very important area, which is called, normally we use this term gate. Flow cytometry is synonymous with gating. But what is this gate? What is regions? We'll see now. Any doubts with what we discussed till now? Super, crystal clear. Now let's go with regions and gates. So when you see a data, this is a data with a side scatter CD45. Okay, so you have a cluster here, which is lymphocyte. You have a cluster here, which is likely a monocyte, and you have a cluster here, which is neutrophil. Okay, now you find these three clusters. Now what is a region is, now I'm interested in only studying the lymphocyte. So this is my first plot. So I told you some universal plots, right? First is for stable acquisition, you use time plot. Then you use forward scatter and side scatter to select the viable cells. Then you use a singlet plot. Then you use side scatter CD45 plot. So these are all universal plots. So if you do any analysis, these 3 plots or 4 plots should be always there as your first plots. So similar to this is a site scatter CD45 and this is lymphocytes, monocytes and neutrophils. Now I'm interested only in the lymphocytes for my further analysis. I'm not bothered about neutrophils or monocytes, which is not I'm interested, because my experiment is dealing only with lymphocytes. So I need to take this lymphocyte for further analysis. Now what I do is I draw a region. I draw a small drawing around this particular population. Okay, I'll show you during our analysis. Okay, so this is something like the one which you're drawing, a shape that is drawn around this particular population is called selecting a region. That is called region. Okay, normally what people do is when they draw a region around this population, they call that as gating. That is not gating. When I draw a shape to select this population, it is called region. Okay, I am drawing a region around this population. Okay, now what is a gate is when I am applying this particular population in another plot so that only this particular population is shown in that, then it is called gating. Okay, so I'll tell you what. Now see, this is again side scatter and forward scatter. Now I'm interested only in lymphocytes. So when I'm drawing a shape which may be polygonal or oval or square or rectangle or anything, when I'm drawing a shape around this particular population, selecting it, that is called region. Okay, that is called a region. So okay, when do you so whenever I'm drawing a shape around this particular population or selecting that particular population gets a different color. Okay, say if as I draw it, it turned into a red color, so that particular population and all the other plots will be turning red in color. Okay, now when do you say the name gate is when I'm selecting this R1 population and I'm putting it on a CD4 CD8 plot. Now what happens is only this particular population will be displayed. The other populations will not be displayed. You see, this is the CD4 CD8 plot where all the populations are shown. Okay, but when I use this particular region and gate it in CD4 CD8, only that particular population is seen. That is called gating. I'll tell you what, you just meet a flow cytometry person, ask him what is this name. You just draw a shape around a population of interest and ask him what is its name. He will say this is called gating. No, that is not gating. Selecting a population alone does not mean gating. Gating is when you select a population by drawing a shape which is called a region. When you drop that region in a subsequent plot so that only that particular population, only this population is shown in that, then it is called gating. Understood? So I have seen most of the people who have not gone through the basics, even I'm now parallelly taking advanced. Okay, so when I ask someone like, what am I doing? They say, sir, you're gating. No, that is not gating. I am just drawing a region. I am putting a region around that population of interest. That is called region. When I'm putting that region in a different plot, okay, or say for example, in this case, a CD4 CD8 plot, so that only that population is seen, that is called gating this population across CD4 CD8. Then it is called, then you should use the word gating. But now, as you become experienced and so, we use this term interchangeably. We say like, that's a gating marker, you gate this population. But this is actual flow cytometry language, this is the correct one. Okay, so I want you to know this. Okay, so regions are shapes that are drawn around a population of interest on a one, which is an histogram or a 2-parameter plot. Okay, when a region is used to limit the cells, okay, when a region is used to limit the cells which is there inside it, okay, to limit the cells that are drawn on a plot, okay, that is termed as gate. So when you're using this region to limit the cells that are drawn on a plot, it's called gating. So R1 is being gated on 4 and 8 plot here. Okay, so everyone understood this? For example, here you see region R1 has been drawn around the lymphocyte cluster. Mostly people call this as gating. That is not gating. So R1 has been drawn around the lymphocyte cluster in the scatter plot. The computer has colored the cells region. So whenever you draw a region around a population of interest, the color of that particular cells changes across all the plots. Okay, automatically it changes. The color, I'll show you during the analysis. The computer has colored the cells in region red. The color identifies the lymphocyte in the plot of CD4, CD8. This approach sometimes called color gating. Okay. So region R1 can also be used to set a gate on CD4 versus CD8 plot. Okay, that is the computer is instructed to show the cells that fall in the R1 and all cells falling outside R1 are ignored. So when I'm selecting this particular population and putting in CD4, CD8, only this population will be displayed, and then only I can call gating. Okay, so that is it about gating. So now if I want to select only the viable cells, now I'm drawing a region like this. But most people say this is a viability gate. Okay, this is called region. So I am selecting a region, and when I use this viable cells within this region in a singlet plot, that is called gating the viable cells. Okay, so that is called gating. So I suppose everyone understood what is region and what is gating, correct? Anyone has a doubt? Anyone has a doubt? So clear, right? So I'll go ahead. Thank you. So what are the types of gates? Now your software has multiple things. See, this is how it has been now. It's more interchangeably, okay? So now, so what are the tools available to select a region? So you have a linear gate or something linear thing. Then you have a quadrant. So I told you this, right? Even quadrants can be used as to select a population for gating. Okay, then the most commonly used is a polygonal gate, which is a freehand gate drawn. Then is a rectangle gate where you can select the population by just dragging a rectangle. Then you have an elliptical gate. Then you have a Boolean gate. Boolean gate is something like a equation. You can select the population by giving an equation. Say for example, I need this population and not that population. Only that population will be selected. That is called Boolean gate. And then auto gate. This is software driven. Based on the density, the gate will be the region will be drawn automatically. That is called auto gate. I'll give you examples, right? Now this is a size scatter CD45 plot. Now how does a polygonal gate look like? This is a polygonal gate where I manually draw a region around this particular population of interest. This is a polygonal gate. Now how does a rectangle gate looks? This is how a rectangle gate looks, which I don't commonly use because populations are not that well shaped and well defined. Okay, I need to move based on the population which I need to select. Rectangle is something like by default it comes only rectangle. People who have, like during live analysis, you let me know, I'll show you everything. Okay, then this is elliptical gate where you select the population with an elliptical region. Then this is a linear gate where you select the population in an histogram. In an histogram, you use a linear gate. In an histogram, you select something with a linear gate. Okay. This is not used in dot plots where there are more than one parameter. Then this is an auto gate because when I keep the cursor here, after selecting the auto gate, if I keep the cursor here, directly that population will be selected based on the density. So this is not, I have not drawn this gate. It has selected by itself. This is called auto gates. This is software driven. Okay. So now coming to what is hierarchical gating. Hierarchical gating is from selecting one population, you get that population in the second plot. So then that particular gate will, so for example, I'll tell you here. Now this is forward scatter, side scatter. You have selected the viable cells. Okay. Now you draw a region around this. Now you get this particular population in the height versus area, singlet plot. Now you again draw a region including only the singlets and excluding the doublets. Now you get the singlets in the next plot, which is side scatter CD45. Okay, now you are eliminating 45 bright population and selecting populations. This is a viability plot. Okay, this is a viability plot. So you are selecting cells which are viable. Okay, you are selecting or drawing. You are drawing a region across populations which are only viable, excluding the dead cells. Then the live cells are dropped in CD side scatter CD45, and you now draw a region around the lymphocytes. Now this particular region will be used as a gate for side scatter CD3, and now you select only the CD3 cells or the T cells, and now the T cells are used to gate on CD4 versus 8 in the final plot. Okay, so going like this from sequential manner is called hierarchical gating. And this is called, when you put a tree plot, it will show you from which population has come from which population. If I put a tree plot, it will show like CD4 has come from CD3, CD3 has come from CD45 bright, CD45 bright has come from live population, live has come from singlet, singlets has come from scatter. So this way of sequential gating is called hierarchical gating, from top to bottom. Okay, so ungated, then you select this, then only this is applied, this particular population is gated on height versus area singlet plot, then select the singlet, and only singlet is gated on side scatter viability dyne, then only viable cells are gated on side scatter CD45 to select lymphocytes, then lymphocytes are gated on side scatter CD3 to select T cells are gated on 4 and 8. This is called sequential hierarchical gating. Now there is called something called back gating, BACK, back gating, where I'll tell you what. Now if I want to see where this particular CD4 positive population is falling in the forward scatter side scatter plot, I want to see where this particular population is falling in the side scatter viability or side scatter CD45. That is called backgating. So going in a reverse fashion. So you select this population and you use this particular population and gate it on a scatter parameter or a parameter which you have seen before, especially a scatter parameter, that is called backgating. So this is sequential forward gating from one by one. And then finally, if you want to, before you sign off, you want to check whether where this population is actually lying in the scatter plot or any other previously used plots. That is called backgating. Okay, so you select a region and gate it on a scatter parameter or previously used plot. That is called backgating. Okay, normally backgating is done on scatter plots. Okay. Any doubts? Are you all clear? Any doubts till now? Are you people there? It's all clear, right? So no doubts, right? Yeah. Perfect. So now this is called backgating. So this is what I explained you till now. So in normal practice, regions are drawn on scatter parameters. So if you see the first one, regions are drawn around scatter parameters. That is how you do, right? So first you use time plot, then first plot you use is a scatter plot, forward scatter, side scatter for viable cells. So regions are drawn across scatter parameters, and it is used to set a gate on fluorescent parameters. When you do the ulta, that is you select a region on fluorescent parameter and gate it on scatter parameter, that is called backgating. However, occasionally it is unclear as to where the region should be drawn. In such cases, the region can be often be drawn on a fluorescent parameters which defines the population of interest, and the region is used to set a gate on light scatter plot. That is called as backgating. Okay. So for example, if you want to see where the CD4 positive helper cells is falling in forward scatter side scatter plot, that is called backgating. You select CD4 positive population and then gate it on forward scatter side scatter plot. That is called backgating. Okay. Now see, what is the overlay? I told you something called overlay, right? Overlay is to compare two histograms or two dot plots to check the intensity of two different populations. Two different populations across, for example, now this is the lymphocyte expression for HLA-ABC in a patient, and this is a lymphocyte expression of ABC in a control. Okay, now I want to check whether the patient is showing adequate HLA-ABC as the control. So I want to check whether the intensity of HLA-ABC in lymphocyte in this patient is same as that shown in the control. Now I can able to overlay these two histograms like this. This is called overlay. By overlaying, now I can able to see that the patient lymphocyte HLA-ABC expression is slightly lower compared to the control. Okay, so this is the use of overlay. Of course, I can able to see it by median fluorescent intensity, which is possible, but overlay gives you a better way and easy way of checking whether it is adequate or slightly low or slightly higher or very high or very low. So just overlapping is over imposing two populations over each other to check whether there is adequate expression or there is no or it is either dim or something like that. Okay, is that clear? Overlay. Then we are coming to something very important. The software what you are using will give you beautiful statistics. Many people use this, right? You will say percentage population, so you need not calculate it. The percentage of cells expressing that particular marker, total number of cells, which is, if you have a population of interest, how much is the percentage of that population among the total cells? These all you can see it in software. Similarly, when you are saying a marker is positive and you want to know the intensity, specific, the perfect intensity, like which we call it as fluorescent intensity. Okay, median fluorescent intensity or mean fluorescent intensity. That all can be obtained by statistics, which is available in the software. You need not calculate manually. If you are doing it manually, it is very difficult. Okay. Now you check this. So now A is there. Once I draw a region around that particular population, and when I click right click on a tab opens like this. Now if I select the percentage total, that gives me what is the percentage of lymphocytes among all the populations. Okay. Similarly, if I'm gated, it means like how much percentage of lymphocytes are there in this particular plot alone. Okay, so similarly, if I've added beads, if I click cells per microliter, it will give the absolute counts of the lymphocytes. Similarly, if I want to see the intensity of CD45 in the lymphocytes, if I just press median, it will give you the MFI, median fluorescent intensity. So there are multiple statistics available for you: median, arithmetic mean, mode, standard deviation, CV, half peak CV, all these things are available. Okay, so that is, we have a bunch of statistics available and it will be useful for you. Okay, see now, I've just selected the intensity. X median means that if A is a population which I have drawn a region around, right? So A is lymphocytes. So the intensity of CD45, the lymphocyte, the lymphocyte expresses CD45 with an intensity of MFI is 86.84. The same lymphocytes is showing side scatter intensity of 109.23. Okay, so you can get this MFI. You would have come across this term MFI, median fluorescent intensity. So that is a value which you can get from the software. Okay, so coming to the other part, how do you describe the markers, especially when you are doing leukemia, lymphoma, or any qualitative analysis? Okay, qualitative analysis. Okay, now you can express your markers easily as positive or negative. So there is no need for you to give that particular, if it is positive, there is no need for you to give that positive as a percentage, or there is also no need for you to call that positive by intensity, whether it is dim positive, whether it is bright positive, or it is moderate positive. All you need to say is whether that particular population is positive or negative for that marker. So either plus or minus. Okay, so that is one way of expressing the markers. Okay, which is binary. Yes or no, positive or negative, that's it. But most of your flow cytometric analysis, you need to interpret the positivity based on the intensity. You have to further classify positivity based on the intensity. So which is maybe dim, bright, moderate, or variable. And you should also sometimes need to give the percentage of that population expressing that marker. Okay, so the positivity sometimes has to be given with these two manner. I mean, it has to be discussed in these two specific categories: percentage of cells expressing that marker, and also the intensity of that marker in the cells, positive cells. So this also has to be reported. So how do you do this? I'll tell you an example. Now, the example for this first one, describing markers, my expression of markers. Now, this is a good experiment, HLA-B27. So what I need to do is to check whether the lymphocytes are showing HLA-B27 or not. Okay, so you know what is HLA-B27? HLA-B27 is a MHC class 1 molecule. Okay, so patients with expressing MHC class 1 molecule, HLA-B27 specifically, are more prone for ankylosing spondylitis. Okay, now that's what the clinician asks you. So what you do is you just gate the lymphocytes and check whether this particular MHC molecule, HLA-B27, is present in the lymphocytes or not. If it is present, it's normal. If it is absent, it is abnormal. Okay, sorry. If it is this particular allele, if it is positive, it's abnormal. If it is negative, it is fine. Okay, because the patients who's having this HLA-B27 allele are more prone for ankylosing spondylitis. Okay, so I gate the lymphocytes. See, I've gated. See, again, I'm using the word gated. So I'm drawing a region around lymphocytes, and I'm gating this lymphocyte on HLA-B27, which is in the y-axis. Okay. Now, if the population lies in this quadrant, it means like it is negative for HLA-B27. Okay. If the population is lying in this quadrant, it means like it is positive for HLA-B27. So this is actually HLA-B27 fixing. I have not put HLA-B27 here. Okay. So this is positive. So this way of putting the data, either it is positive or negative, okay, is one type of assay. And HLA-B27 is a very good example for that. But apart from HLA-B27, most of your other assays, qualitative assays like leukemia, lymphoma, immunophenotyping, and so, apart from telling it positive, you need to tell the percentage of cells which is positive, and also you need to say what is the intensity of positivity for that particular marker. And how do you do this? I'll tell you. Till now, any doubts? Are you all clear? Any doubts? No doubts. Right. I'm sorry. I'm sorry. Right. Let's go. Now, just assume that, and you need to start tell the expression of markers based on the internal positive and negative control. For example, now let's assume we are analyzing a case of leukemia and lymphoma. So you are analyzing a marker CD19 in the blast. Okay, it is not enough if you say just the blast are positive for CD19. You can't just say that and stop. You cannot say. You should comment on the intensity of CD19 in the blast. Okay, and how do you do that? Let's see. This is a schematic diagram what I have made for your better understanding. So for CD19, what would be the internal positive control? Someone?
B lymphocyte.
B lymphocyte. Okay, and what would be the internal negative control? Anything apart from B lymphocytes, right? Your T cells likely. So you need to interpret your blast population with these two populations, with the help of these two populations. Say for example, if the blast is lying right in the, okay, just if you are a beginner, just draw a small region around these two populations. Now, if your blast is falling right on this region of negative internal control, then it is negative, no doubt. Similarly, if the blast population is falling in the region you made with the positive internal control, which is normal B cells, then you call it as moderate expression of CD19. Then you call it as moderate expression of CD19 in the target population. Other study population or the blast. If the blast is falling much more on the right side away from the region what you have drawn with the internal positive control, that is, it is falling on the much on the right side, then it has much high intensity of CD19 compared to the normal B cells, then you call it as bright. Now the blast is having bright CD19 expression. Now, if the blast population or the target population is lying in between your internal negative and internal positive control, just in between both of them, then you call it as dim. Okay, you call that the blast is expressing dim CD19. Now, if you have the blast falling like this in a stretched fashion, which is traversing from the negative region to the positive region, then you call it as variable or heterogeneous. Okay. Now, if the same blast, if you find to split into two populations, one falling in the negative region and one falling in the positive region in a dimmer fashion, then I would call this as partial dim. I would call this as partial dim. If the same, again, if I have two populations, one is falling in the negative, one is falling in this particular area, I call partial moderate. When I have two populations, one is falling here, one is falling here, I would call partial bright. Okay, so that is how you need to interpret your markers with respect to internal controls. This is a much easier way and a much reproducible way of expressing the intensity of markers in the target population. See, there is also one other, what do you call this as? Now you have a population of interest which is 50% or somewhere falling in the negative region and a part of it is falling in the positive region in a very dim fashion. Then you call it as
variable.
No, you will not call it as variable. Variable is something like I told you now, from negative it has to go till the positive region. This one I call it as dim to negative.
Okay.
Dim to negative. Okay, variable, it should at least come till this area. Okay. So this is very easy and reproducible way of doing it, and I do this way and many people do this way. And there was also one more article which was published to comment on the intensity based on this, and this is quite confusing and I don't want you to follow this, but if you want I can just go through that. This is based on the histograms by the peaks. Okay, so and you can't draw histograms for every plot, right? So it's very difficult for you to follow this. So if the red is the population, target population, and the blue is the negative control. Here they are only interested in the negative control. So if the blast population histogram is overlapping with the negative control, then it's negative. And if it's overlapping and still a small subset is positive in a dimmer fashion, you still call it as negative. Is that what they say? And when you have the positive population histogram slightly in the move to right compared to the histogram, you need to see the peaks here, peaks of the histogram. Here is the negative peak and here is the positive peak. So it is slightly moved, then you call it as weak, positive or dim. And again here the peak, though it lies with the negative control, you see a population greater than 10% in the positive area, dim area, then you call it as dim, because here it's less than 10%, here it is greater than 10% but less than 50%. So you call it as dim. Okay, then partial positive is what, like you have two subsets. One subset peak is falls with the negative peak, whereas another population peak is clearly in the positive region, then you call it as partial positive. Similarly, this is another population where I would call it as variable, but they call it as partial positive one. And there is two clearly separated blast population, one falling with the negative control and one clearly away. Then you call again this as partial positive. Okay. Okay. Now strong positive, the criteria they say is like this population should be wide, should not overlap with the negative control. The peak should not overlap with each other, and there should be a gap in between, and then you call it as bright. If there is no gap, then you call it as moderate or medium. Okay, heterogeneous is where, as we saw, from the negative it trails to the positive population. Okay, so it could be heterogeneous this way or this way. Okay, see, I'm not going very deep into this because I'll tell you what, this is very tough to follow. Okay, so this is the very easier and a much reliable, reproducible method of expressing the markers, because during leukemia lymphoma you cannot draw histograms for each marker with negative. You can't do this, so you will do reporting for 2-3 hours for one case. Okay, now I've spoke much. Now you need to speak. I'll tell you the population. You tell me what is it like. Okay, now you have a normal B cells which are green in color, and you have a normal T cells which are red in color. Now this is the population which we need to comment on the intensity, okay, of all the markers. Okay, now you need to tell me. Ready? So those of you want to say, you can just unmute and you can reply. So what is the intensity of 19 in this population?
So moderate to bright.
See, 19 is in which axis? Y axis, correct?
Yeah.
So your internal control is B lymphocyte, which is here, correct? You just check with the intensity, compare this and this. Is it bright? Is it going beyond this?
No, sir.
No, right? So bright is not the way. If you see, it is lying parallelly, or if you see, it is slightly lower than that of CD19, normal B cells. The 19 expression in the normal population is slightly lower compared to the normal B cells, right? So I would call this as dim CD19. Okay, or you can call this dim to moderate CD19. Okay, now how about this particular population for CD5? 5 is in the x-axis. So you have a positive control.
Bright.
Why bright? See, now, dim. See, CD5 is in the x-axis. You have an internal positive control here and a negative control here. Okay. Now this population is falling in between that, both of them. So I would call this dim. Only when it falls here, I would call CD5 bright. Okay. Now let's go with, let's go, 20. 20, you have a good positive control. 20 is in y-axis. You have an internal positive control, which is normal B cells, and you have a negative control T cells, which are lying in the double negative region. And the abnormal population or the population of interest is here. So what is its intensity for CD20?
Positive.
See, you should not say positive. Everyone knows it's positive. Dim positive.
Dim
Positive.
positive.
Okay. Very good. How about CD22? It's in the x-axis.
It is also dim.
Very good. Excellent. Okay. And see, this is an hinge gate. See, this is a hinge quadrant. You see this hinge quadrant, okay? Because sometimes kappa lambda, you cannot draw a strict linear quadrant. So this is an hinge gate, and this is kappa restricted CLL population, okay? And 23, you don't have an internal positive control at all. Sometimes you will be having this problem. Okay, but here with experience, you will learn that this is CD23, likely bright. Okay, so now you know how to interpret the markers, correct? So coming to the conclusion, before you start your analysis, ensure you have got a stable acquisition. Exclude the debris and doublets. So I told you this universal plots, right? First stable acquisition with time plot. Then you need to draw the the viable gate, which is with side scatter, forward scatter plot. Then singlet plot. Then side scatter CD45 plot. For all people who are doing clinical cytometry, these 4 plots should be there. Okay. Data should be within the scale. So when it is out of the scale, change it to by exponential scale and build the population within the scale. Okay. When you are acquiring, you can increase or decrease the voltage, but only for scatter parameters, not for fluorescent parameters. If you are changing the voltage for fluorescent parameters, then you need to do compensation again. Okay, so this should not be done after compensation. Okay, but for scatter parameters you can do, but for fluorescent parameters you should not do that. Okay, the data should be well compensated. Check for all possible positive and negative controls. This is very important. Don't ever just, whenever people ask my opinion on some of their plots, they'll send me the plots only with the blast. But how do I know what, I mean, like without any controls? So there should be an internal positive controls gated along with the lymphocytes. That will help me to interpret the marker. Okay, so this is how it is. So sample acquisition using instrument. So once it is acquired, in the acquisition software you will have the file. Then you will be transporting the FCS file. The file is saved in a dedicated server or a study file. You will keep, of course your computer will save. Once it's overloaded, you can copy in a hard disk. Then that particular file will be transferred to another system. Again, you can analyze in the same acquisition software, but we normally analyze in a third-party software, which has extra advantages and features. Then we analyze that, and then we save the PDF of the report. That PDF will be uploaded in the LIS, and then it will be report. I mean, it can be dispatched, and a copy of it will be archived. So that's how our lab works. So most of the labs work in the same manner. With that, I'll just conclude, and before we end the session, I'll just show you a case on how to see. So there's a question from Dr. Anand. Sir, please explain height, area, and shift plot. Okay. So okay. So see, for every signal which has been taken up by the detector, a bell curve is formed. Okay. Now this signal has multiple discriminant, like multiple multiple parameters. Okay, so this particular signal can be described in multiple discriminators. Okay, something like area of the pulse, which is the total area under the curve. Okay, so it's the total area. The other thing is height of the pulse, which is related to the brightness of the signal, and of course area is also related to the proportional to the brightness of the signal. And then you have the width of the pulse. So these are the three things which comes with a signal. So similarly, when you have a forward scatter or a fluorescence, a scatter parameter or a fluorescence parameter, every parameter will be denoted with that particular things. Like for example, forward scatter area, forward scatter height, forward scatter width, something like that. Okay, so that is about the things. So I'll just show you a case now, and then so this is Kaluza. Okay, I'll just drag that file. Okay. Okay. So let's delete everything. Let's start from the beginning so that you will have a clarity. So this is the software. This is an analysis software called Kaluza. Okay. So people who want to try this, you can download the trial version, and I'll share that a person who's related to this or the application person in the group. You can contact him, and he will help you in downloading the trial software, which you can use it for 1 month. Okay. Now let me show you what are the features. So I showed you this. These are plots and tables where you have an histogram, dot plot, tree plot, radar plot, density, contour, and I showed you what is overlay. Okay. These three I don't commonly use, which is comparison, cell cycle. I don't do cell cycle analysis and commonly so.
So
Any
your
doubt?
screen is not visible. So it,
Oh my God. Hold on. My screen is not visible, right? Okay, I'm sorry. I have to put a screen sharing. I'm sorry. Thanks for letting me know that. Is it visible now?
Yes, sir.
Yes, sir.
Perfect. Thanks for letting me know that. Okay, right. Now see, this is a third-party Kaluza software, which is from Beckman Coulter. As I said, I would request all of you to download this. It's a bit a stringy process, but still give some time to download it. I'll just share the number of a person who's help you in downloading this. Please work with some files. I'll be sharing some files in the upcoming talks, because that is all more related to analysis. So we'll be having stem cell enumeration. We'll be having lymphocyte subset analysis. We'll have PNH. So there I'll be sharing you the files so you can work on it, so that you have an hands-on experience. Okay, so this is the software, and as I discussed, these are the plots. You have histograms, dot plot, tree, radar plot, density plot, so and so. Okay, then you have gates and tools. So as I said, you have multiple gating options. You can use a linear gate, a quadrant. You can put a quadrant. You can use an inch quadrant. You can use a polygonal gate, rectangle gate, a boolean gate, elliptical gate, and a auto gate. Now you can also do post acquisition compensation with this particular tab, which is there. Okay, I'll just show you first how these are done. Okay, now see, to select a plot, what you need to do, just go to the plots and tables, select a plot. What plot you want? You want a dot plot? Select a dot plot. Okay, now you will get a dot plot. So dot plot, you can put two parameters, one on the x and one in the y axis. So what I'll do, I'll just put R, one of the first plots for checking whether there's a stable acquisition. So this is a time plot, and it shows stable acquisition. There is no break in between. Okay, so that is it. Now the second plot is singlet plot. So singlet plot, I'll show you in density plot. Okay, so for singlet, I need to select. So when I select forward scatter, you see okay, I have disabled it. You see here, now forward scatter has peak, which is height. Forward scatter has INT, which is area. Then forward scatter has time of flight. So similarly, side scatter also has this, but we have disabled it because I'm not going to use it. When I'm going to include all those things, even the file size becomes much bigger. So I've ignored it for side scatter and all other fluorescent parameters. But if I enable it, even side scatter will have peak, integral, time of flight. And similarly, FL1, FL2, all these fluorescent channels will also have these three parts of the pulse signal. Okay, but I'm not interested in it, so I have just ignored it. Okay. Now FS peak is height. Okay, height is otherwise called FS peak. Similarly, area is otherwise called integral. Okay, FS peak versus FS INT. Okay, now I'm getting two populations. One is a singlet and the other is some few doublets. I can also see what I'm doing, increasing and decreasing the resolution so that you can see the thing. Okay. So I'm just gating this. Okay. And excluding this particular. So I'm drawing a region here. So see, even I am using that word gate. Okay. But even you can use it, but if someone asks you what is the difference between region and gate, you should be able to say. So I've drawn a region around the singlet. Now the next plot, I'll just draw. Which plot can I show you? I'll show you again because the other plots may not be very useful. So now,
Excuse me, sir.
sorry, yeah.
So if the singlet shows rocketing, then it is not to be compensated.
No. Singlets will always show rocketing.
Okay, sir.
Singlets will always show rocketing. I thought like you are going to hold me with like, sir, why you went to singlet before viability gate? I shouldn't do that, right? Second is I need to draw a viability. But anyhow, okay, now I'm just drawing a viability gate, selecting the populations which are viable. So I'm eliminating the populations which are dead. So as I'm drawing a region, the color automatically changes. Okay, you can change the color as per your billing. Okay, so I'm eliminating some populations here, which is debris, which is a population with very low forward scatter and side scatter, likely to be some RBC debris or some other platelet or some other debris. I'm not interested in this, so I'm eliminating it. Now I'm getting this viable population, viable region on the singlet gate. Okay, now I've got a singlet population. So next I'll draw another gate here. I'll just put the singlet population. So this is called hierarchical gating. So from this, in the ungated population, I've selected the population which is viable, and I've gated the viable population in the forward scatter peak and forward scatter area to get the singlets. Then I've gated the singlets in the side scatter CD45. This is called hierarchical gating. Okay. So I'm getting this now. Okay. So you're finding two clusters. One is a lymphocyte cluster, and another is a neutrophil cluster, likely. The neutrophil is showing slightly lower side scatter, but still fine. So now I'm selecting only the lymphocytes. Okay. Now, see, this is an histogram. So when I select histogram, by default, count comes on the y-axis. Okay. Now, what I'll do, but still I can change it since I have the option. So I'll just check sites. Let me check how much B lymphocytes and T lymphocytes are there. So CD5 on y-axis and CD19 on x-axis. And I'm getting only the lymphocytes which I'm interested on. Okay. See, this is what I told you. Now, so I'll show you the same thing. I'll just put O here. And I'm going to select two markers. 5, I'm selecting in linear scale. 19, I'm going to select in linear scale. And I'm dropping, see how the population looks. Because it's a fluorescent parameter, and if you put it in linear scale, this is how it looks. Okay, now let me put it in log scale. So CD19 in log scale and CD5 in log scale. Now the population is looking like this. Am I happy with the population? No, I'm not happy with the population. Okay, because some population is buried here. Similarly, there is some population which is buried here. So the better way is to put a logical scale where I can able to pull out that population. See, when I put logical, you see that this part becomes a linear. So similarly, I'll change this to linear, logical, which is a by exponential scale. Logical is also called by exponential scale, in log scale. So when I put here, you see here, this becomes a linear scale up to this cursor, and here it becomes a log scale after this particular pointer. Now what I can do, I can able to pull this population. Similarly, I can able to pull this population. Now you see all the populations have come into the scale. Okay. Now I'll gate. So I have multiple options to gate. See, if I'm missing something, please let me know, because I may forget some things. And later in the night, I will remember that I didn't describe that. Okay. So let me know if I'm missing something. And see, there are multiple ways of gating. Okay. So one is, I told you, a polygonal gate, which is a linear manual gating like this. Manually selecting the region. Okay. This is called polygonal gate. Now there is one more population. I'll use a rectangle gate. Rectangle is something like I cannot draw it. I can put like this. This is how I use a rectangle gate. Then you have elliptical gate where you can select the population like this in this manner. And there is something called auto gate here. So this will automatically gate based on the density. See, something like that. I've just selected it. As I go near the population, it's getting it automatically. So this is called auto gate. So these are the different gating tools available for you. Boolean is something like you need to give an equation. For example, if I select this Boolean gate, okay, I select new gate and I give an equation. For example, how in the sense, say in the other next plot, I want only the population which are T cells and the normal B cells. I don't want the other population. So what I'll do, I'll just select Boolean gate. Then I'll say, what are the gate names? R and S. R and S. Okay. So I'll say R or if you want to add both, you need to select or and or S. Okay. Now this becomes a gate with W. Now if I drop W in the same CD5 versus CD19, you see only these two populations will be being shown. So that is about Boolean. Boolean is again you give instruction which population you want to take, and it will show you only that population. Okay. Now, so I have explained you about the plots. I need to show you an overlay. Okay. So let me do that a bit later. Then gates I've covered. Okay. Compensation. Okay, I'll try to check with some compensation. Is there any compensation problem? Yeah, there is a compensation. See, now I'm dragging the population. This is compensated. Actually, I've compensated already. So compensation, like you need to select this population and then you can adjust. See, now this is not compensated. So you can adjust the compensation until it is adequately compensated. Now the data is correctly compensated. Now it's looking fine. So you can also do post-acquisition compensation like this. Okay. Now let's start with analysis. Okay. Now, which is the abnormal population here? Is it R? Is it T? It is S or U? Which is the abnormal population?
U.
Why? Why it is abnormal?
Because it is positive for
Positive
CD5 and
5 and 19.
both.
Very good. So it's a B cell marker. It's CD19 is positive and it is expressing CD5. So that can't be a normal population at all. And when it is a form, so there can be some CD19 positive population which can express CD5, but it can't be such a huge population in a normal setting. And you want to check how much is the percentage of this population. So then now the role of statistics will come into play. So what you need to do, you just keep the cursor there, right click on it, then you get a dialog box like this. Okay, each has a different function. For example, now if I select this, I can able to cut the plot, copy this plot, delete this plot, something like that. Then I can able to change the colors using this plot. Then I can able to do scaling changes in this plot. And these are gating tools and all. Now I'm worried about the statistics, right? So I'll go for this percentage sign, which tells me about the thing. So now I select this and I select how much of that U is among the total population. So if I select that, okay, so the total population among all is 46.85%. 46.85% is the abnormal population, percentage of abnormal population among all the nucleated cells. Okay, so that's how you use the percentages. If you want to see how much is the normal T cells there, again you click on it, percentage total. Similarly, you can also do that. Okay, so 8.74% is normal T cells. Similarly, normal B cells. Okay, now I want to check how is the CD5 intensity in the neoplastic cells. This is the case of CLL. Okay, you know CLL is CD5 positive, 23 positive. Even mantle is CD5 positive, but it is 23 negative. This is the CLL case which I'm using to show the demo. So I want to check how is the intensity of CD5 in the neoplastic cells. Okay, so how is the intensity? What do you want to call that as? So you can directly, if you are experienced, you can call it by here. But now since beginners, I'll just put, and I'll put the internal and the negative control. Okay. Now what you do, use a quadrant. Okay. Just use a quadrant to set your negative limit for CD5. Okay. I can use this particular gate, the lymphocyte gate O. Okay. So there's something like this. So what do you want to call now? So this is this. See, you have your green. I'll put the green here. So we'll do it step by step. Don't worry. So we have a green here. So I'll draw a region around this green. Okay. And you have for a negative control, I'll just drop S, which is my B lymphocyte. Okay, so I'll draw a region around that particular population. Okay, so I can able to draw a quadrant with respect to the negative control to set the negative limit. I don't have any y-axis marker, so this particular thing will not be very useful. So I'm just lifting it up. Now I'll draw the neoplastic population, which is U. Yes. Now you tell me what is the intensity?
So moderate.
Moderate positive. Okay, it's more likely moderate. CD5 is moderate positive. Okay, so that's how you need to comment on the intensity of markers. Okay, now someone is asking you what is the median fluorescent intensity of CD5 in this particular population. Okay, so now I need to check the MFI. So what I'm going to do, I'm going to gate this particular population, select this gate this population on this plot with CD5. Okay, so now automatically this population comes. Now, if I want to check the median fluorescent intensity, I need to right click, go to the statistics and select median or mode, whatever you want. I'll select median fluorescent intensity. So it is 35.79 is the MFI. And someone asked me to compare that with normal lymphocytes, MFI of normal lymphocytes. Now, normal lymphocytes are here, R. So I'll just drop R. Then I'll select similarly and drop this. So now what is the median fluorescent intensity? So it is 51.54. So it is, of course, looks moderate, but the intensity is slightly lower compared to normal T cells. Okay. Now, how do you want to check whether how is this population? I can use an overlay. Now, if I overlay these two histograms, this will tell me how the population is there. Is it dim or is it same? Okay. So what I need to do, I just need to drag with pressing an Alt key. I'm dropping here, and now I'm dropping the T cells. Now you see, this is how the population is. So as we saw, it is almost moderate. It is overlapping with each other, but still a part of T cells are still on the brighter side. Like it is more than that of neoplastic cells. So that's how you do an overlay. Okay. If you want to bring in one more population, say for example, let's bring in a negative control S. So what I'll do, I'll just drop S here, and I'll also pull that here in the overlay that acts as a negative control. So it's falling here because that is smaller in size because the size of the population is so small. Okay. Okay. So that is about statistics, overlays. What else should I say? Have I covered? Any doubts? So have I covered all the features? And this has multiple other things. For example, I can able to take color of the population, some populations which is disturbing me. So I can take the colors, that is called color precedence. Then I can able to import and export compensations. This is called compensation matrix. Lecture 4, we had a compensation matrix. So I can able to import different compensation setting to this experiment. I can export this particular compensation matrix to another experiment. So I can do all these things. These are all software features which is there with the analysis software, which may not be there with your acquisition software. Any other doubts? Any doubts? If you have no doubts, then we can conclude the session.
So what is the use of overlay?
So use of overlay is to just check, to compare two populations. See now, see this one, if I want to just compare the neoplastic cells with negative or positive control, I can just check with overlay. As simple as that. But again, if you ask me, sir, I can do that with a dot plot. Yeah, you can do it with a dot plot. Some population, what happens is that the differences may not be quite well visible with the dot plot. Okay, in that case, an overlay can help you, but again, it doesn't have a very great use. I don't use it, but I just want to show you a feature that overlay is there. So I showed you.
Okay, sir.
Yeah. Any other doubts?
Sir, please show backgating.
Excellent. That is what I like. So yes, that's an excellent question. So see, this is what the forward gating is all about. So time plot, then I've selected this. I've put this gate on this, A on this, and O I have selected. And from O, I've taken T lymphocytes, some NK cells. So it is negative for T and B. So it should be likely NK cells or some other monocyte population spillover. And this is the neoplastic cells, and this is normal B cells. Now I want to check where does this neoplastic B cells is lying in the forward side scatter plot. Is it lying in the lymphocyte region? I want to confirm. I have a doubt now whether the population what I gated is right. So now what I need to do is, I'll remove this. Now I need to put a forward scatter and side scatter. Okay, and then when I'm going to put that population U here, so it's already U. So if I put this population here, now I'm getting where this particular population is falling. This is called backgating. Or you can see it in ungated area also. See, this is called backgating. Backgating is somewhere like this is forward gating. So this population putting similarly if you can put it in side scatter CD45 where the population is falling, that is also backgating. See, this is also, so you can just put that population. This is called backgating. Now I'll show you one more thing, kappa lambda and the use of hinge quadrant. Okay, now this is double negative I feel. Let's see. This is kappa lambda. Okay, now this population is like this. This is neoplastic population. Show it is monoclonal. It's a monoclonal population showing positive to only one of the light chains. So I'll use a control to draw a quadrant. Yes, this is my normal B cells. Correct? Normal B cells. So I'm using normal B cells in kappa lambda plot. So since it's normal, it's splitting into two. A kappa population and a lambda population. Okay. Now I need to draw a gate. So normally for kappa lambda, we will not use a gate like this. We will not use like this. We will use something called a hinge gate, which I described. Okay, you need to draw a hinge gate like this. Okay, now I have drawn a gate like hinge gate like this. Now what I need to do, I need to drop that neoplastic population U. So now you see that the neoplastic population is exhibiting kappa and it is negative for lambda and it is a monoclonal population, confirming its neoplastic nature. Okay, that is about the hinge quadrant. Any other doubts? Any other doubts? No doubts.
Sir, what is the meaning of restriction related to kappa or lambda restriction, sir?
You want to like percentage?
Restriction, sir, when we are using kappa or lambda restriction. What does it mean, sir, actually?
What does that mean? Okay. See, that is something about more things. See, okay. So now, see, restriction means, see, normal B cells, okay, when they are getting formed, some may be kappa, some may be lambda. Okay. So when you see here, if you see normal B cells, you see some cells showing kappa light chain and some cells showing lambda light chain. But when a neoplastic clone arises, it's a clonal population, right? That is, one cell becomes 2, 2 becomes 4, 4 becomes 8. So it's arising from a single cell, and that's what we call it as clonal. So these neoplastic cells will be either kappa, fully expressing kappa, or fully expressing lambda. It will not split like this. So in this case, if I put this neoplastic population, it is all completely kappa positive. That is what I called kappa restricted, and it is lambda negative. So that is confirming its clonality, monoclonal population. It's a neoplastic population. Any other doubts?
Okay, sir, thank you.
Thanks a lot. Bye. Happy weekend. We'll meet next. I want an important announcement to be made. See, now we are due for assessment 2. That's a very great news for you, for those who were there. And however, I'll be putting in the group also. We are due for assessment 2. But assessment 2 is likely to happen next week. But because of a small engagement with the work I have, I'll be postponing that assessment to the week after the next. So next week we'll be going with the lecture, which is stem cell enumeration. Okay. So assessment week will be the week next to the week after the next week. Okay. I'll anyhow put it in the group. So thanks a lot. Take care. Bye. Good night.
Thank
and
you
have
so
a
much.
happy weekend. Bye.